Welcome back, everyone. In this video, we will look at different examples of supervised learning algorithms in practice. The majority of algorithms that I'm going to show you today are implemented in scikit-learn, which is a free and open source machine learning library in Python. Many of you, I assume, know it already, but let's get into it. So, first of all, during this video, we will use the iris flower dataset in all our examples. The iris flower dataset is also known as Fisher's iris flower dataset and is a multivariate dataset popularized by British statistician and biologist Ronald Fisher. It is a very old dataset, but it is a classic one. I assume that maybe some of you know it already. If not, you're gonna get acquainted with it today. This dataset contains 50 samples from each of the three species of iris, so altogether 150 samples. You will see them in a second. They are called iris setosa, iris virginica, and iris versicolor. And there are four characteristics which are measured for each sample. We have the sepal length and width, and the petal length and width for every flower. So altogether four. All measures are in centimeters. I encourage you to go and look what's a sepal and what's a petal. If you don't remember from biology, I'm not a biologist, so I'm not going to get into it. Um, so what Fisher did using this combination of four features is that he created a linear discriminant model to differentiate between these species. But let's start with linear regression, our first algorithm. And what we do essentially in the beginning is that we import all the usual suspects and then scikit-learn. So we have matplotlib, numpy, pandas, seaborn, you've seen this before, and then a few packages from scikit-learn dataset so that we can import our dataset, this linear model that we might use later on, then the mean squared error, the R2 score, mean absolute error that we're going to use later on as well for checking how good our linear regression was, then the linear regression model that we're going to use as well, and this package which allows us to split the dataset into train and test datasets. So first of all, we load the dataset after we import all these libraries. So that's the first step. Okay, that's done. And then what we do, we would like to create a data frame and then check a little bit of statistical analysis. So we create in the data frame. And I printed here the feature names and the target names. So these are the type of iris. These are the features that we can get from the data set. This is the description of the data set. So you can see the count, you can see the mean, the standard deviation, mean, max, and so on. If you want to get a little bit more info about this data set, you can check this out. So essentially, there are five features, and one of the four of them are of numeric type, and one is an object type. And this will need to be changed for future purposes, probably in numeric. So what we can do next is we could visualize the relationships between variables, and for that we can use a pair plot, which can be done very easily in a line of code, as you see here in Seaborn. So, okay, this will take a bit, but not too long, so just bear with me. All right, so now we have the pair plot. So what you can see here on the diagonal, right? We can see a distribution on each of the variables, and then off the diagonal, we can see the relationships between variables as scatter plots, right? And what you look for usually is some positive and negative correlations between variables, also in the scatter plot. So then you can look at stuff like clusters, like you have the one here, or at outliers, like you have these ones. over here. And in general, it's good to check the distribution of the data. This might come in handy later on. Even if nothing really catches your attention now, it's good to get back to this kind of graph later on and check it out. But now let's get into business. Oh, before that, another thing that you can do to check the distribution of the data is you can also create this type of box plots, maybe for each of the features that you're interested in, right? So the sepal length and width and the petal length and width. Then you can see as well the distribution in this form. You can see the outliers. What you can do here, there are different type of plots, of course, that you can do to visualize the data set. You can also create violin plots. I also encourage you to look for those. And those violin plots are very similar to these box plots, but also they have the distribution of the data. So it's a lot easier maybe to interpret it. They're not extremely popular outside bioinformatics, but in bioinformatics, for instance, they're really, really used a lot. Now we convert our last feature into numerical type. And what we want to do with this linear regression is that we want to predict the sepal length of the iris flowers based on the rest of the features. So you recall that we had our linear regression model, and then we have the response variable y and the independent variables in x. So we load them into these two variables, and that's what we want to do, is to split the dataset so that we're able to train the algorithm on the training part of the dataset on one part of it, and then to test it on another part of it that essentially the algorithm hasn't seen before. So for this, we use this train test split method to divide our data into features and labels, essentially. So X train and Y train sets are used for training and fitting the model, these two. And then X test and Y test sets are used for testing the model that we're predicting afterwards, right? And then we can explicitly test the size of the train and the test set. So sometimes you can also write your own function that does this, so you don't necessarily have to use this. But what it is important to remember is to split it in a way that makes sense. So usually there is no mathematical formula which tells you exactly what you need to split it in, but a 25-75, a 20-80 is something that we do usually in machine learning. So here the test size of 0.25 over here means that 25 of the data goes into the test sets and the rest into the training. And this random state parameter is used only for data reproducibility, for instance, so that you get the same result every time you're running the algorithm. So what we do next is over here, we instantiate the linear regression model, right? And then we train this model on our train set, and we're making the predictions. And after we predicted this, we would like to evaluate the model's performance. And there are different performance evaluations for linear regression. There are means absolute error, mean squared error, and mean root squared error. Mean absolute error is the average absolute difference between the predicted values and the actual values. So we're always comparing predicted and actual values, and it's measured in the same units as the target variable. The lower the MAE is, so the lower the mean absolute error is, the better the model fit is. This is not so sensitive to outliers, unfortunately. So this is one problem. Then we have the mean squared error, which is the average squared difference between predicted and actual values. A lower mean squared error also indicates a better fit. but the mean squared error penalizes more heavily the outliers than the MAE. And then we have the mean root square error, which is the same units as well as the target variable. This is the root square of the mean squared error, essentially. And similar to the other two, the lower it is, the better the model is. And it's often preferred because it's easier to understand usually in this context than the other two. What we expect here is to have in the mean root square error between 0.2 and 0.5 is usually a good model, right? So now if we run this after I talked this much, we can say that the mean square error is 0.3, which means that it's kind of like an okay model to have. Remember that this is not a big data set, it's only 150 entries. So I would say that it's actually, considering the data set is quite an okay prediction. Then the next algorithm that we would like to look at is the naive Bayes. So we import the usual libraries that we've learned about already. And then we import this Gaussian naive Bayes, which is a package from scikit-learn. And then also we can import this metrics package accuracy score. And I would like to remind everyone, even though I mentioned it many times, that naive Bayes assumes that the features are independent of each other. Now, if we check here, okay, so we're loading the dataset first, and we're creating a data frame as we do, and then we would like to see how correlated to each other the features are. And for that, we are creating this kind of a correlation heat map like we have here. And usually we would like to have them not highly correlated because this algorithm actually considers them that they're not correlated with high correlation. So this is not the case here, but we're going to go on with this example anyway. And what we do is that we, again, split it in test and train, and we create this Gaussian NB model, and then we're gonna fit our model on that. So let's do that. So you remember that this is a classification algorithm. So what we want to calculate is the probability for all three flower classes, right? So we aim to classify flowers of these three types: Setosa, Versicolor, Virginica. And after we trained the model, we can check the prediction of the model, and then we would like to create confusion matrix because it's good to check between the actual values and the predicted values for the model. And we can see, based on this, that the model worked perfectly. The accuracy is essentially 100%, and everything was predicted as expected. So we can see that all of these are 0 and all the diagonal is like this. So this was the Bayes algorithm. And now we're going to go to logistic regression. So what I would like to remind everyone about logistic regression, even though I mentioned it many times already, the aim of this algorithm is classification. So the name of regression might be a little deceiving here. A comparison with a linear regression you can find in the previous video when we discussed about more theoretical aspects of supervised learning. But what do we do here? Well, so far we import a bunch of libraries we are going to use throughout the training and predicting stage and also for visualization. So I'm not going to go into them again because they're all the same, essentially, very similar. Um, but a very important thing to do here with this algorithm is feature scaling, and I'm gonna tell you a little bit about it now. So what feature scaling does is essentially just a pre-processing method which standardizes the range of features in the dataset. And why this is important is because features with significantly different scales can affect what algorithms do. For example, during training, a model may give more weight to features that have larger values. So features with larger values get prioritized, even if they are less relevant, actually. And scaling ensures that all these features have an equal impact on the model's learning process, right? Um, you have to remember that algorithms in machine learning, I mean, that employ this kind of gradient descent as an optimization strategy, so linear regression, logistic regression, neural networks, they all require data to be scaled. We didn't do it for linear regression, but it is good to do so anyways. But just before we get into the actual training of the model, what I would like to do is to plot the relationships between each feature and each species. So we do it over here. Let's see how this works. Uh-huh. Okay, so we have here three different species, as you can see, Virginica, versicolor, and setosa, and then all the feature for the species. And you can see already from here that the features alone can classify the species most probably. So now if we fit the model on the trace set and predict it on the test set, what I would like to do afterwards, after this, is to create a confusion matrix. Um, because in the confusion matrix we can see which entities was misclassified, how many of them, and so on. So we do again the splitting, we do the feature scaling, we feed the logistic regression to the training set, we predict the test results, and then we predict the probabilities, and then we just print the results, the precision, recall, the F1 score, and then the confusion matrix with Seaborn. So now if we look at the results look really good. We have 96% accuracy essentially, and only one instance was misclassified. So overall, this is a very good result. And this confusion matrix, it's really easy to see what was misclassified and where, and how can you, in bigger models, not maybe in this small example, but you can think about what you can change in the model or in the data in order to obtain better performance. So it's good to remember. And the next model we are going to look at is the k-nearest neighbors algorithm. And for this, we are actually going to get a little bit into um, creating this kind of uh, decision boundaries so that we see how the algorithm has worked. So you remember this is also a classification algorithm. So what we want to do is to classify the dataset and then, like I said earlier on, draw the decision boundaries of the clusters. But in order to do that, what we have to do is, first of all, to decide on the number of neighbors, right? Which for us is 16. We import these libraries that we're gonna need later on, and we import the dataset. We load the dataset actually, like I said. And what I would like to do is to only take two features for the first features for simplicity, and then we set up the coloring, right? So we take the features, we set up the coloring, and then this is going to be a little bit more complicated part of the code, but let's get into it. So what we're doing here, we're trying to set up the k-nearest neighbors model and prepare to visualize the decision boundaries, right? So we iterate through two different weighing schemes. the uniform and the distance one, right? And then we calculate the boundaries for the plot. So for the uniform one, for this one, all the points in each neighborhood are weighed equally. And then for the distance one, this one weighs the points by the inverse of their distance. So closer neighbors have a greater influence on the classification. And what we do next is then we proceed to the model fitting. So we call this classifier and we fit the model. And then after we fit the model, based on the data, we define the boundaries of the feature columns, essentially, which is over here. Then we create a mesh grid. And after we create the mesh grid, we predict classes for the mesh grid points over here with a classifier that we feed the data to before that. Then we put the prediction in a plot and we add the scatter plots of the points so that we see what's also what points are in each cluster, right? So if we run this code, this is also taking a little bit, but not too much. So we have a 3-class classification. We see the 3 different clusters, and we have this kind of K here, 15 that we chose earlier on, and we have different weights, like I said, for uniform weighting and for distance. And if you want to see, we don't know really at this moment with what we did so far, we do not know if this is the best K that we can get. We don't know if this is the best 3-class classification that we can get. Maybe there are better boundaries than this. So if you want to see what is the best K, then you can try to calculate it with different values of these neighbors and then calculate for each neighbor what is the smallest misclassification error, right? So you calculate the misclassification error and it's essentially you go through a for loop and then you see which is the best K for you. And now if we go to the last but not least, to the random forest. So essentially what a random forest does is it fits a number of decision tree classifiers on different subsamples of the dataset. And then it uses averaging to improve the predictive accuracy. And also it controls overfitting, which is really great. So what we need to do is to, again, we define our target, which is the species, and then our features, which is everything else in the iris dataset minus the species. So all the other sepal length, width, petal length, width in the features. And after we run this, then we can import this random forest classifier from scikit-learn. We create a random forest classifier object where we have the number of estimators. This means the number of trees that are going to be included, the number of decision trees that are going to be included in our random forest classifier. And there's this criterion tells us the quality of the split. So if we run this, we're going to fit our model. And what we can do here is to print the accuracy to see how well it worked. What we predicted. Wait a second. Yeah, so I realized that I haven't actually instantiated that YPred anywhere, but then I have to do it here. And then calculate the accuracy based on that. So the accuracy is 98%, which is really good. And then what we could do here as well, based on this, we can calculate what are the most important features. So first we get the feature importance right from this kind of object. Then we can create a data frame and then we can display them. And also if we want to display them in a nicer way, then we can just plot a bar plot with them. which looks like this. So the petal width seems to be the most important feature, and then the petal length, the second most important. All right, so this was the hands-on for this week, and see you in the next video.